All right, so welcome back to the OneClass channel. So my name is Joey. I'm going to be your chemistry teacher for the next hour or so. We had our session 2 hours ago. What we did was we answered kind of typical chemistry questions that were asked in kind of between grade 10 all the way up to the organic chemistry university level. So what we're going to do is we're going to continue with that session as well. So I have a bunch of questions ranging from, I believe, I have university, some grade 11, grade 12, and organic chemistry problems as well. So kind of following in terms of that format. If you're tuning in for the first time, thank you so much for tuning in. Thank you so much for watching. What we're doing here at OneClass, if you're new to this channel, is that we are providing kind of online solutions and kind of videos and live streams for frequently asked questions in both mathematics and in chemistry. So that's kind of our motive for and our goal here at OneClass. And me as a OneClass teacher, what I'm doing is I'm verifying solutions for you so that you have kind of the best answers going towards your classes in the future or your classes in the present as well. So just a little bit about myself. My name is Joey. I'm currently a secondary school educator in Ontario, and my teachable subjects are chemistry and as well as mathematics. I'm working towards a mathematics teachable as well. So without further ado, let's get started. I have about 11 questions again for this hour, and let's see how much we get done for the session here. So let's get started. So our first question is asking us, a 0.22 caliber handgun fires a 1.9 gram bullet at a velocity of 765 meters per second. Calculate the de Broglie wavelength of a bullet. Is the wave nature of matter significant for bullets? Okay, so this answer is very, very incomplete. I don't know there's no numbers here. There's nothing here. I think the grammar is kind of off. So solution's obviously incorrect or it's incomplete here. So I'm going to write solutions incomplete. But let's solve this problem here. So I have here a 0.22 caliber handgun, right? So let's say this is question one. Let's see, question one here. Let's see if my pen is working. There we go. Question one's asking, so I have a 1.9 gram bullet, and it reaches a velocity of v equals 765 meters per second, and it says calculate, I want the wavelength, the de Broglie wavelength. So this is lambda here, and this is going to be our wavelength of the bullet here. So what do we need to know? Well, we have to figure out what the we know our de Broglie equation here, right? So the de Broglie wave equation basically states that lambda, or the wavelength, equals h, which is Planck's constant, divided by mass times our speed, right? So here is our de Broglie wave equation. It's basically derived from kind of Planck's equation as well, like E equals hc over lambda. And if we rearrange that, de Broglie just found a relationship between the mass and also the energy with those two kind of components, and basically he developed this kind of equation as well. So lambda equals h over mv, and we want to solve for lambda. So this is actually really good. So we want to solve for lambda here, and I have so lambda is already on the left side here. Planck's constant is 6.63 times 10 to the negative 34. So I'm going to say here, and some calculators might have that already inputted, but I'm writing down here 6.63 times 10 to the negative 34. This will be in joules per second here. Is the unit for kind of this equation here. So joules per second, 6.63 times 10 to the negative 34 joules per second. My mass here is actually in kilograms. So what I'm going to have to do is I'm going to have to convert my grams into kilograms, right? So I have 1.9 grams here. I'm going to divide this by 1,000, right? So let me divide this by 1,000. So it's 1 kg. So 1,000 grams in 1 kilogram. I'm going to use my calculator. 1.9 divided by 1,000 equals 1.9 times 10 to the negative 3. So I'm going to write 1.9 times 10 to the negative 3 kilograms here. I'm going to multiply that by the speed, right, which we have given 765 meters per second here. And then this here should equals meters, right? Should equal meters per second here, just because my kilograms times meters per second, or times meters, will give us meters per second squared will give us our joules here, right? So this here would cancel out, and we would basically get our wavelength here. So let me just input this into our calculator here. So So we have 6.63 times 10 to the negative 34 as our numerator. Then we're going to divide it by 1.9 times 10 to the negative 3 kilograms times 765 meters per second. And we're going to get a value of, this is 4.56 times 10 to the negative 34 here. So I'm going to keep I'll keep 2 decimal places, because again, 1.9 states I have 2 significant digits. So this would be 4.6 here. 4.6 times 10 to the negative 34 meters here. And this here is the wavelength of my wavelength of the bullet. So this is the de Broglie wavelength. So here's my solution here. And it's asking us, the second part of the question is asking us, is the wave nature of matter significant for bullets? And in this case, it's not really significant. Like, this doesn't really tell me anything here. It doesn't tell me if I emit some sort of light. It doesn't, in terms of the spectra. If we were talking about electrons here, obviously the speed would be much, much faster, probably about the speed of light, which is 3 times 10 to 8 meters per second here. But again, this speed is very, very slow, right? If we have a very, very slow speed, we're going to get a very, very small wavelength. And this wavelength doesn't really tell us anything about about the bullet here. So in this case, it doesn't, it's because the wavelength here, it says the de Broglie wavelength of the bullet is very small, so it's going to be basically neglected, actually. So its wave nature is not significant for the bullet. Remember, wave particle duality states that we have particles can exist as a wave here, so in terms of wavelength, and can also exist as a particle, so it also has a mass here, right? So again, the mass here is much more important. Like 1.9 grams bullet, we 1.9 grams, we can measure that, right? If we can measure that, then I guess the opposite is the wavelength here. The wavelength property of the bullet is basically not significant, just because it's so small. So I'm gonna say here solution here is incomplete. Incomplete because no answer was given. And I'm going to say here de Broglie, I'm going to write here de Broglie wavelength equals Planck's constant, so H over m times v. So this is Planck's constant divided by mass of bullet. Maybe put parenthesis around this one. These guys here, mass of bullet times the speed of the bullet, and then basically this would equal, I'm going to just keep my formatting here, so this is 6.63 times 10 to the negative 34 divided by, this here is 1.9 times 10 to the negative 3 kilograms multiplied by 765 meters per second, and we get a value of 4.6 times 10 to the negative 34 meters. De Broglie wavelength of the bullet is extremely small, therefore not significant. The wave nature of the bullet is not significant. So I'm going to say solution here is incorrect just because because no answer was given here. So I'm going to write solution here is incorrect.